Part 3, Lecture 1. We will be talking about confounding, something we already touched on in the previous lecture. As always, let's start with an example. Comparison of mean FVC, forced vital capacity, something that you measure during spirometry, among 20 persons who recently joined an exercise gymnasium. 10 had no experience carrying out any exercises, whereas the other 10 had some experience doing exercises at home. Forced vital capacity was measured on each of the 20 individuals. The mean FVC was compared between the two groups. Okay, a quick refresher on the SAS data set creation. In this case, we are referring to temporary SAS datasets, and those are the ones that when you code for it in your SAS program, it will create a dataset and put it in the folder called work. Beware that when you turn off your computer or when you exit SAS, anything in the work folder will be lost. And so just keep that in mind. The rest of it here, just read through this slide. This is just a reminder of stuff that we've already gone through. Never hurts to remind yourself of it though. Okay, here's our data set. We're starting with unpaired. In this case, as you've seen before, here's our input statement. The $sign refers to characters in this variable. An interesting little twist here. Exer is the yes, no, but as in 0, 1, so it's a number. That's the reason we don't have the $sign. But then we create a variable called exercise, where if, so basically we're saying exercise equals yes, but if exer equals 0, then overwrite exercise with no. And what this does is it creates now a character variable for exercise yes, no. Here's the next example where we're creating basically the same data set, but it's now paired. The input variables are the same as well as the exercise, but in this case, the ID for paired values goes from 1 to 10, of course, because there are only 10 pairs. And in the previous example, we had ID going from 1 to 20 because we had 20 patients. So let's start off with the paired data set. Now, if you have paired data, what you're naturally going to think of doing is taking the difference between the pairs and looking to see if that difference is greater than 0. The mean difference is greater than 0. And so this is what we're doing here. We're creating another data set called pairs, where we take the first value and the second value for FVC. We create a variable called dFVC, which is the difference. We actually perform the difference. Here's the data lines, which are going to be your pairs of data. So this is FVC1, this is FVC2, this is FVC1, this is FVC2, as you know, etc. And then we use proc means, of course, to get our mean. So we're going to get the mean FVC1 at mean FVC2 and the mean of the difference. All right, let's look at the output from our proc means statement. Here's the three variables, FVC1, FVC2, difference in FVC. Of course, n equals 10 for all three. Here are your means. It's a negative difference here, but that's just because of the way the variables FVC1 and 2 were ordered. Here's your variance and your standard deviation. We're going to want to test to see whether or not this difference is significantly different from 0. This is what the proc t-test when you use the paired statement is for. Here's your two variables, of course. We're also going to look at the correlation between your FVC1 and FVC2, because as we know, if you look at the calculation for the variance or the equation for the variance of the difference, it includes, as we've already covered, the correlation here, which if there was no correlation, this drops out and it's literally just the sum of the variance. Alrighty, so here are the results for your proc t-test and your proc core. So proc t-test, here's that same difference that we observed in the proc means results. Here's the calculation for your standard error. Here's your t-value, which is a -4 basically, and it is statistically significant, 0.0032, which means that it is significantly different than 0. If you look at the correlation procedure here, we're looking at the correlation between FVC1 and FVC2. This is a Pearson correlation. If you look at the Pearson's R, it's basically 0.7, which is that's a good strong correlation, moderately strong, sorry, with a significant p-value. So this means that the correlation is going to be playing in the calculation of the variance of the difference. Now let's have a look at proc GLM, which we went through in the last lecture, and you guys are experts now. So here's the simple code, proc GLM. We're using the same dataset pairs. In this model, though, we would like to see if there's a linear relationship between FVC and FVC1 and FVC2. Here's the output. You'll note here that there's type 1 sums of squares and type 3 sums of squares. If you remember, it's because here I didn't specify SS3, which would mean only show me sums of squares 3. So it gives you by default both. Where do we look? Of course, type 3 sums of squares. You look at your p-value. Oh, that looks familiar, 0.0259. And here's your estimate. Okay, this is your parameter estimate, is 0.53. Now you're going to say, this looks fairly familiar here, this p-value. So hang on to that thought. Here is the slope of the line, right? So you have beta naught, which is your intercept, plus beta 1, which is your coefficient for your slope, times FVC1, which is your independent variable. And the slope in this case is 0.531, which is given here by this estimate. Okay. Now, interestingly, if you look here, you have the R square. Remember, we've talked about the R square, which is the amount or the percent variability in the dependent variable that is accounted for by the model. And in this case, it's 48%. Now, interestingly, if you take the square root of the R square, which you'll end up with R, it's going to be equal to 0.69. And if you remember from the previous slide, when we did proc core for Pearson correlation, the R was 0.69 and the p-value was 0.0259. Interesting. So this is a special case for simple regression. So simple regression, when you only have one independent variable with, of course, one dependent variable. In this special case, the Pearson correlation will be, or the R for the Pearson correlation will be the square root of the R square of your model, but that this only occurs when you have what's called a simple regression. If you have multiple variable regression, it doesn't work anymore, and we'll probably touch on that a little bit later on in the course. Okay, so we've now just completed this first way of testing a paired data set where we have manually taken the difference between the two measures per subject and checked to see whether or not the mean difference was significantly different from zero, our null hypothesis. But if you want to start working with more interesting models, you're going to have to work with proc GLM. And so let's have a look here. This is similarly a paired data set, but this is the first one we actually created in this lecture. And it is a paired data set, FVC once again, but in this case, the grouping is exercise yes, no. If you remember correctly, the full exercise variable is the one that actually is a class variable that has two levels, yes and no, and that's why it's included in the class statement. Okay, let's look at the output. So the first output here, you'll see here right away is, interestingly, I only get type 3 sums of squares, and that's because I only asked for it in the statement, the model statement. First thing I'm going to point out is your p-value for exercise is significant. So there is a difference in FVC whether or not you exercise. If we look at the least square means, which we asked for, which is once again basically a t-test, right? Paired comparison t-test. Once again here we're showing that there is a significant difference between the two. No surprise. The difference between these two here, you'll see this is an F test, an F value here when you're doing an ANOVA, but this is a t-test, so you're going to get a t-statistic, which is the t-value. If you look here, this is your limits for your confidence interval. They do not include 0 and therefore not surprisingly, your p-value is less than 0.05. All right, let's switch gears a little bit. So let's look at the student t-test for comparison of unpaired means. So we just did paired means. Great. That was very straightforward. Now we're going to do the same thing, but we're going to use the unpaired data set. So in this case, we have 20 measures, 20 independent measures, 10 that are from exercise yes and 10 from exercise no. As you know the code, you guys are experts now, very straightforward. Here's your output, okay? You're going to look, everyone does, right? Oh, is it significant? So you go to your p-value, yes. And in this case, both are. So pooled and scatter weight. Remember we were talking about equality of variance. So let's have a peek at that. They're both almost identical, almost the same. So this would assume that really because there's no difference, most probably the variances are equal or not significantly different. And that is the case. This is confirmed here in equality of variances. Your p-value is not significant, and that means that the variances are not found to be significantly different. Now, just this f value is interesting here. This f value is your test. Is your test to see whether or not the variances are equal or not. And so how do we calculate that? It's actually quite straightforward. Here's the standard deviations, okay, for the mean of your two levels of exercise, no and yes. If you take the square of these and then divide them, ta-da, that is your F ratio. This is not something you have to remember. This is just showing you some statistics. You can come back to this later and go, oh, wow, that's cool. Okay, t-test for comparing unpaired means. Check, we've done it. Unpaired, right? Here's your class variable for exercise. Here's your variable of interest, FVC, and we just did it. We just went through it. Easy. But what if you want a little more complicated model? What do? You guys know now, you go to proc GLM. And in this case, same thing. Data is unpaired. Very similar. Look at this. Class exercise, FVC equals exercise. Oh, I'm only specifying sums of squares type 3. Good. And as usual, the LS means, which is going to confirm our t-test with our probability for the t-test as well, and the standard error and the confidence limits. Okay, here are the results. As always, your ANOVA pops out first. We've only asked for sums of squares type 3, and that's all we've got. You'll see here the p-value looks very familiar. It's the same p-value that we got for the pooled variance t-test. And oh, look at that. It's confirmed again over here when we ask for the least square means, which does a t-test, and we get the same t-value and probability as we did when we did the t-test. Here are your confidence limits for the means. Here's the confidence limits for your difference, as we saw previously in the t-test as well. Now, as it turns out, the previous data sets also had the height of each of the 20 subjects. And what if we were concerned that maybe height was associated with FVC? And how do we deal with that? Okay, so the first thing we're going to do is we're going to look to see whether the mean height between those that exercise and those that do not is significantly different. So that's easy. You guys are experts now. We just do proc t-test on the unpaired data set for exercise as the class variable, but now we're looking at height. The next thing we can do is we can look at to see whether or not there's a relationship between height and FVC. In this case, we're going to do it by level of exercise. We could have put exercise here, or exer would have done the same thing. But in this case, we're going to look at, so the output is going to give us two outputs, one for exercise yes and the other for exercise no, for the relationship between height and FVC. We can then do our full model, okay, here, where we have, once again, class exercise, model is output is outcome, sorry, is FVC. This time, though, we're going to, of course, exercise yes, no. That's our group variable, which we're interested in the comparison. But this time, oh, look at that. We're going to include height, and we're also going to include the interaction term for exercise and height. And once again, we're only interested in sums of squares type 3. All right, first output from our t-test. Remember, the outcome is height in this case, and we're comparing between the two levels of exercise, which means yes and no. If we look at the p-value, it is not significant. And therefore, is mean height different between those who exercise and those who don't? It would appear no, yet there is a difference, observed difference of 12.9 centimeters, as you can see here, between the two groups, but it's not statistically significant. Okay, next output. This is PROC-GLM. Dependent variable is FEC, but in this case, when exercise is 0, so those 10 subjects that did not exercise, and we want to see the relationship with height. If you look at the R-square, it's 85%. That's pretty good. Is the slope different than 0? Yes, and it's significantly. So that means there is a linear relationship between height and FEC for those that do not exercise. Okay, and just as a reminder, if you take your sums of squares for the model, you divide them by the total sums of squares, this is how you get your R-square, which is reported here. That's just a refresher. Okay, same output. This time, though, we're looking at the level for exercise. Yes, the 10 subjects who did exercise. You'll immediately note that when you do that same calculation of the sums of squares model over the total sums of squares, that your R-square is only 62%, which is less than for those that did not exercise. Once again, is the slope significantly different from 0? Yes, it is. So there is a linear relationship between height and FEC. Okay, let's put them together. So when you look at the two equations for the straight lines, for whether there was, the subjects that did not exercise versus the subjects that did exercise, here are your points. So the red points are for yes, I exercised, and blue for the no, I did not exercise. And here are the two lines. Now you'll see that the slopes are, they look actually, they're not identical, but they're quite similar, but that the red line is above the blue line. So those that do exercise, on average, the mean FEC is going to be higher than for those that do not exercise. Okay, so here is our more exciting model where we combine everything together. So you'll remember the outcome is the same, FEC. However, in this case, we're looking at exercise, we're looking at height, and we're looking at height crossed exercise, so the interaction term at the same time. Now, right away, you can see, the interaction term is not significant. So that is an interesting thing to note immediately, because what it should indicate to you is that the relationship between FEC and height does not differ whether you exercise or you don't. So that means the lines that we just saw in the previous slide are parallel. Or, if you wish, the difference in parallelism between the two lines is not significantly different. How about that? That's what this not being significant indicates. Let's have a look at the equation for this interaction model. Now, the predicted FEC, we're going to call FECP. Height, of course, short, as you know, is HGT. Exercise can be 0 or 1, which is essentially no or yes. Now, here's the full equation. Your predicted FEC is going to be your intercept, your beta naught, plus your beta 1, which is your coefficient for the exercise variable in your model, plus the beta 2, the coefficient for your height variable in the model, plus beta 3, your coefficient for the interaction term in your model, exercise times height. Now, what you can do is go back to the previous slide, look up those coefficients, beta naught, beta 1, beta 2, beta 3, and just replace them here, and voila, there is your interaction model for FEC. So now that we have the equation for the interaction model, What we can now do is look at the difference for when you are exercising or when you are not exercising. Now you'll remember that when we use the variable exer, you have 0 for no exercise, 1 for exercise. Now if we had used the variable exercise and put it in the class variable, SAS will do exactly that for you. It will assign a 0 and a 1 to your levels for exercise. So if you look at when exercise is equal to 0 and you replace it in the equation, well, these terms drop out. And what do you have left? You have the line equation for when you're not exercising, and its predicted FVC is minus 3.35 plus 0.04 times height. There's your line that we saw 3 slides ago when we were comparing the two slopes that we got from the separate GLMs for exercise versus no exercise. Now it's a little bit different for when there is exercise, because it's 1, and so these terms don't drop out. They remain, of course, because you're multiplying by 1. And when you simplify, you now get predicted FVC equals negative 4.36, basically, plus 0.04 times height. Interestingly, when you take the coefficients for height from the two different slopes and you subtract them, you end up with 0.0041, which is, it turns out, the coefficient for the interaction term, so B3. And so the interaction term coefficient is actually the difference between the slopes, and that's why what we're doing is we're testing to see whether or not the difference between the slopes is significantly different from 0. And if it is, then the two slopes are different. If it's not, then they're not different. And what you then do is you can't say the interaction is significant and can remain in the model, so then you remove it from the model. So this is what we've done here in this model. We have, of course, FVC as our dependent variable, but as independent variables, we've only included exercise and height and not the interaction term, because we found that the interaction term is not significant. When we do this, and we look at, for instance, the graph of the output, you have, yes, once again, the two lines, the two straight line, and their equations, which we just calculated in the previous slide. And here you'll see, though, that the two lines are perfectly parallel. And the reason for that is because we've excluded the interaction term. And because of that, we're assuming that they are actually parallel because we've excluded the interaction term. And you'll note, for that reason, these numbers are slightly different, and the reason for that is because we did not include the interaction term in the model, so the model did not account for that third variable in the model, and so all of these numbers just change slightly to reflect these two lines being perfectly parallel. If you flip back a bunch of slides, you'll look at the figure, and you'll see that these two lines are not quite parallel, but they're just not significantly different from being parallel. Important to note, if you look at exercise as your group variable, it is not significant. So the difference between exercise, yes, no, in FVC, when adjusting for height in your model, is no longer significant. If you flip back a few slides and you look at our t-test, you'll see that it was significant, but it is no longer significant. So here is a perfect example of a confounding effect of height on our ability to show the difference in FVC between exercise, yes and no. So that was a lot to digest in a short number of slides, and what I recommend you do is just flip through the slides back and forth, and check the progression of what we did in order for you to understand how we got to the conclusion that when you adjust for height, that the difference in FVC between the two groups of those that exercise and those that do not exercise is not statistically significant. And the reason for that is height is not only associated with the outcome, which is FVC, but there's also a small imbalance in height between the two levels of your grouping variable, exercise in this case. And interestingly, we showed that that difference was not statistically significant. However, the actual difference was sufficient to have height act as a confounder in your model.